In this video, we're going to learn how to solve second-order non-homogeneous differential equations with constant coefficients using the method of undetermined coefficients. We'll start by talking about the types of equations that you can solve using this method and what the general solution looks like. We'll then go over the steps that you can follow and how to choose the correct form for the particular solution. We'll then go over 6 examples so that you can see how this method works for all different types of functions. Let's get started. The method of undetermined coefficients is most commonly used to solve second-order non-homogeneous equations like this one down here. And the right-hand side of this equation that we'll call g of x is either a polynomial, an exponential function, a sine or cosine function, or a combination of these functions. G of x is called the non-homogeneous term, or it's also called the forcing function or the input function. The solution to this non-homogeneous equation looks like this. The solution y is equal to y sub c, or it could be y sub h. That's called the complementary solution, or the homogeneous solution, plus y sub p, and that's the particular solution. Y sub c is the solution to the homogeneous equation, and then y sub p is one specific solution to the non-homogeneous equation. When you're solving this type of equation, there are 4 steps that you can follow. The first step is to find y sub c by solving the homogeneous equation that looks like that. The second step is to use the right-hand side that we're calling g of x to determine the appropriate form for the solution y sub p, and then modify it if necessary, depending on what the solution looks like for the homogeneous equation. I'll walk through exactly how to do that. The third step is to find the particular solution by substituting the chosen form back into the non-homogeneous equation that looks like that. And then the last step is to just put it all together and write your final solution as the complementary or homogeneous solution plus the particular solution. Before we walk through all the examples, let's talk briefly about how to choose the form for the particular solution. The form for the particular solution, y sub p, will be of the same form as the right-hand side, g of x. If this form duplicates a term in the homogeneous solution, we have to multiply it by x until it doesn't, and we'll walk through an example of this. If the right-hand side, g of x, is a polynomial that looks like one of these, then the usual form for the particular solution is going to look like this. I'm calling it the usual form because it will need to change if it duplicates the homogeneous solution. If the right-hand side is an exponential function, then the particular solution is going to look like this. And then if it is a sine function or a cosine function, it looks like this. And notice that if it's a sine or a cosine, the particular solution has to have both the sine and the cosine term in it. Let's now walk through 6 examples where we are going to solve a second-order non-homogeneous differential equation. In all these examples, the right-hand side of the equation is either going to be a polynomial, an exponential, a sine or a cosine, or a combination of these functions. Let's look at our first example. In this example, the right-hand side, or the forcing term, is a constant. Our solution is going to be y is equal to the complementary solution plus the particular solution. To find the complementary solution, we need to solve the homogeneous differential equation, and that equation is y double prime minus 2y prime minus 3y is equal to 0. To solve this equation, we are going to substitute in that y is equal to e to the mx, because that's what the general form of the solution looks like. When we plug that in, the exponential ends up canceling out, and we get m squared minus 2m minus 3 is equal to 0. I have a video on solving homogeneous equations just like this if you need to review that. Let's see. We can factor this. It factors as m plus 1 and m minus 3. And that gives us that m is equal to minus 1 and it's equal to 3. We can then write our solution y sub c as c1 e to the minus x plus c2 e to the 3x. Let's go ahead and highlight that because we're going to need that in a minute. For our second step, we are going to find the form for the particular solution. To find the form for y sub p, we need to look at the non-homogeneous equation, and that is y double prime minus 2y prime minus 3y is equal to 5. Because our right-hand side is a constant, we are going to choose the particular solution to be a constant, and I'm going to call that capital A. For step 3, we are going to substitute this solution back into our equation. The first and second derivatives are going to be 0. So we have 0 minus 2 times 0 minus 3 times A, because y is y sub p, which is A, and that's equal to 5. This gives us A is equal to minus 5/3, and then we have y sub p is equal to minus 5/3. That's our particular solution. And then for step 4, we just have to put it all together and we have to add both of our solutions. We get y is equal to y sub c, which was c1 e to the minus x plus c2 e to the 3x. And now we're going to add on our particular solution, which is minus 5/3. And there's our solution. Let's look at our second example. For our second example, our right-hand side for x is a polynomial. Our solution y is going to be y sub c plus y sub p. In step 1, we are going to find y sub c. Notice that the left-hand side is y double prime minus 2y prime minus 3y, and that's the same as our last example. I did that on purpose so that we can just focus in this video on finding the particular solution. Our homogeneous solution is going to be the same as we got in the first example, and it is equal to c1 e to the minus x plus c2 e to the 3x. Now we can move on to step 2, which is to find the form for the particular solution. Let's go ahead and let's write down our non-homogeneous equation. And we're going to choose that our particular solution is a polynomial that matches this form. It is a first-degree polynomial, so y sub p is going to be a plus b times x. Let's go ahead and let's find the first derivative because we're going to have to plug these in. So the first derivative is equal to b, and then our second derivative is equal to 0. Let's plug that back into our equation. So y double prime is 0, and then we have minus 2 times y prime, which is b, and then minus 3 times y, which is a plus bx. And we have a 4x on our right-hand side. Let's combine like terms. I'm going to put all the constants together. And this is minus 3a minus 2b. And then we have a minus 3bx. And then on our right-hand side, I'm going to write this as 0 plus 4 times x. By writing it this way, we can see that minus 3a minus 2b has to be equal to 0, and then minus 3bx has to be equal to 4x. This gives us that minus 3a minus 2b is equal to 0, and we have minus 3b is equal to 4. Let's solve our second equation first. So we get b is equal to minus 4/3, and then let's substitute it back in to our first equation. So we have minus 3a minus 2 times minus 4/3, substituting in for b, is equal to 0. Let's see, this is minus 3a plus 8/3 is equal to 0. So we get minus 3a is minus 8/3, and that gives us that a is equal to 8/9. I think the hardest part in this method is the algebra. If you're going to make a mistake, that's probably where you're going to make it. When I was making this video, I did an algebra mistake and I had to re-record it. And now let's highlight that b is minus 4/3. Now we need to write down our particular solution. Our particular solution, I am looking right up here. I'm going to highlight that in pink. There's our particular solution. And now we know that a is 8/9. And then we add b, which is a minus 4/3 times x. Step 4 is the easiest one. And all we have to do for this one is just combine our two solutions. This gives us y is our homogeneous solution, c1e to the minus x plus c2e to the 3x. And then we add on 8/9 minus 4/3 times x. And there's our solution. In our third example, our right-hand side is an exponential function. Our solution y is again y sub c plus y sub p. In step 1, we're going to write down y sub c. It's the same homogeneous solution as our other two equations. And that solution is c1e to the minus x plus c2e to the 3x. Now in step 2, let's find the particular solution. We're going to base this on our non-homogeneous equation. That's this one right here. Because our right-hand side is an exponential function, the form that we're going to choose for our particular solution is also an exponential function, and it's going to be a times e to the x. This e to the x and that e to the x have to match up. Now let's substitute this expression, a e to the x, back into our non-homogeneous equation. Our first derivative is going to be a e to the x, and then our second derivative is also a e to the x. This gives us a e to the x minus 2a e to the x minus 3a e to the x is equal to 8e to the x. I like when we have an exponential on the right-hand side because I think this one's a little bit easier. Our exponentials are all going to cancel. And let's see, our left-hand side, we have a minus 2a minus 3a. So that is minus 4a. And then we have an 8 on the right-hand side. So our a is equal to minus 2. I just realized that I didn't mark that what we just did was step 3. I think once you get used to a method, you don't even have to think about the numbered steps. You just go through the process. Step 4 is when we are going to combine our solutions. And that gives us y is equal to our homogeneous solution, c1e to the minus x plus c2e to the 3x plus a e to the x. So this is minus 2e to the x. And there's our solution. In example 4, our right-hand side is a trigonometric function. I chose it to be cosine. So this is just an example where you have a sine or a cosine on your right-hand side. Y is going to be equal to y sub c plus y sub p. For step 1, let's write down y sub c. We should have this memorized by now. c1e to the minus x plus c2e to the 3x. And then for step 2, we are going to find our particular solution. We're going to be working with a non-homogeneous equation y double prime minus 2y prime minus 3y is equal to 6 cosine 2x. Because our right-hand side is a cosine or a sine function, our particular solution, y sub p, is going to look like this. It's going to be a times sine, using the same angle that's on the right-hand side, plus b cosine 2x. So if you have a sine or a cosine, your particular solution is going to have a sine and a cosine in it. Let's now go ahead and take our first derivative and then our second derivative. The first derivative is 2a cosine 2x. That extra 2 comes from using the chain rule, minus 2b sine 2x. And then our second derivative, we pick up another 2, so we have a minus 4a sine 2x minus 4b cosine 2x. Now in step 3, we can go ahead and substitute everything back into our equation. Y double prime is minus 4a sine 2x minus 4b cosine 2x minus 2 times y prime, which is 2a cosine 2x minus 2b sine 2x. And then we have a minus 3 times y. So we have a sine 2x plus b cosine 2x. And then the right-hand side is 6 cosine 2x. Let's first combine all of our sine terms. So that's this one, and we have to pick up the negative 2 that's out in front, and then this one. This gives us minus 4a. Minus 2 times minus 2 gives us a plus 4b, and then minus 3a. And that multiplies sine 2x. And now let's pick up our cosine terms. This one, and this one. This gives us a minus 4b minus 4a minus 3b. And that's cosine 2x. And then let's set this equal to 0 times sine 2x plus 6 times cosine 2x. This expression has to be equal to 0, and then this expression has to be equal to 6. Let's go ahead and write these down and combine what's inside our parentheses. We have a minus 4a minus 3a, so this is minus 7a plus 4b, and that's equal to 0. And then we have a minus 4a minus 7b is equal to 6. This is a system of 2 equations and 2 unknowns. There's a lot of different ways we can solve this. I'm just going to use basic algebra, and I am going to say that for this first equation, we can solve for a, and we get 4b is equal to 7a, so that tells us that a is equal to 4 over 7 times b. And then we can substitute that into our second equation. So we have minus 4 times 4 over 7 times b minus 7b is equal to 6. I'm going to multiply everything by 7. So we have minus 16b minus 49b is equal to 42. This gives us minus 65b is equal to 42. So b is equal to minus 42 over 65. That is not very nice, and we actually can't reduce that. Now we can find a. Looking right up here, we can say that a is equal to 4 over 7 times b, which is minus 42 over 65. We'll divide 7 into 42 and we get 6. So this is minus 24 over 65. Now we can write down our particular solution. It is equal to a, which is a minus 24 over 65 times sine 2x. And then b, which is minus 42 over 65 times cosine 2x. Now we can just write down our final solution, and it's y is going to be our homogeneous solution, c1e to the minus x plus c2e to the 3x, and then all we do is copy down our particular solution. And there we have it. That is our solution. In example 5, our right-hand side is minus x e to the 4x. And this is called a combination of functions because we have a polynomial times an exponential. Our solution is again y is equal to yc plus y sub p. In step 1, we are going to write down the homogeneous solution. Yc is equal to c1e to the minus x plus c2e to the 3x. In step 2, we are going to find the particular solution. So let's write down our non-homogeneous equation. Y double prime minus 2y prime minus 3y is equal to minus xe to the 4x. Now we get to choose our particular solution. Because our right-hand side has a polynomial of degree 1 times an exponential, our particular solution has to be a plus b times x, that's a first-degree polynomial, times our exponential, and the power has to be 4x to match the right-hand side. Let's go ahead and take our derivatives. When I was recording this video, this is where I made a mistake, and I had to re-record this part. We have our first, which is a plus bx times the derivative of our second, which is 4e to the 4x, plus our second, e to the 4x, times the derivative of the first, which is b. Before we go to take the second derivative, let's combine stuff. We have 4a plus b plus 4bx. And we multiply that by e to the 4x. Now let's take the second derivative. It's the first, 4a plus b plus 4bx times the derivative of the second, 4e to the 4x, plus the second, e to the 4x, times the derivative of the first, which is just 4b. I'll show you where I made my mistake. I forgot about that little 4 right there. Let's go ahead and combine things. We have 16a plus 4b plus 4b, so we get an 8b plus 16bx. And that gets multiplied by e to the 4x. Now we're all set to go. Let's highlight our y sub p, our yp prime, and our yp double prime, just so we can find them easier. Let's go ahead and substitute this into our non-homogeneous equation. We have 16a plus 8b plus 16bx times e to the 4x minus 2 times yp prime, which is 4a plus b plus 4bx times e to the 4x minus 3 times y, which is a plus bx times e to the 4x. Hang with me, we're almost done. And then our right-hand side is minus x e to the 4x. Let's go ahead and let's cancel out our exponentials. And we'll multiply everything out. We can't forget those constants right there. We have 16a plus 8b plus 16bx minus 8a minus 2b minus 8bx minus 3a minus 3bx. And then on our right-hand side, we have minus x. Let's first combine the constants. That's this, and that. Let's look at the a's first. We have 16 minus 8 minus 3, so that gives us a 5a. And then for the b's, we have 8 minus 2, so that gives us 6. Now let's look at the terms that multiply x. They're all b's, and we have 16 minus 8 minus 3, so that gives us a 5bx. And let's write our right-hand side as 0 minus x. So our constants on the left has to equal our constant of 0 on the right, and then our 5b has to be minus 1. We have 5a plus 6b is equal to 0, and we have that 5b is equal to negative 1. That's nice. So that tells us that b is minus 1 over 5. Let's highlight that. And then we can plug that back into our first equation, and we get 5a is minus 6 times b, which is minus 1/5. So that tells us that a is equal to 6 over 25. I think I didn't allow enough space, so I'm just going to take this and I'm going to move this down a bit. Now we can write down our particular solution. It is equal to a, which is 6 over 25, minus 1/5 times x, that's our bx, times e to the 4x. Almost done. Now we just have to combine things. Y is our homogeneous solution, c1e to the minus x, c2e to the 3x, plus our particular solution, 6 over 25 minus 1 over 5x times e to the 4x. And we did it without making any algebra mistakes. Just remember that you can always check your answer by plugging it back into your original equation. Now let's look at our last example. This example is really important because our right-hand side is actually a duplicate of the homogeneous solution. Our y is equal to yc plus yp. Y sub c is equal to c1e to the minus x plus c2e to the 3x. Notice that the homogeneous solution has an e to the minus x, and our forcing term is e to the minus x. That means that we are going to have to take this into account when we find the form for our particular solution. Let's work on our particular solution now. It's going to be based on y double prime minus 2y prime minus 3y is e to the minus x. The form for our particular solution is not just going to be a e to the minus x. It is going to be a times x times e to the minus x. When the forcing term is the same as the homogeneous solution, you have to multiply by an x. Let's go ahead and take our derivatives. Yp prime is going to be the first times the derivative of the second minus e to the minus x plus the second e to the minus x times the derivative of the first. This gives us a minus a times x, e to the minus x. I always combine it before I take another derivative because that actually saves time. Now we need to differentiate again. We're going to have the first, a minus ax, times the derivative of the second, minus e to the minus x, plus our second, e to the minus x, times the derivative of the first, which is minus a. Let's see. This gives us, we can't forget about that negative right there. So we have minus a, so that's minus 2a, plus ax, e to the minus x. Let's highlight these so we can find them. Now in step 3, we're just going to plug our derivatives back into our equation. We have minus 2a plus ax, e to the minus x, minus 2 times a minus ax, e to the minus x, minus 3 ax e to the minus x, and this is all equal to e to the minus x. Let's go ahead and cross out our exponential, and let's see what we have left. We have minus 2a plus ax minus 2a plus 2ax minus 3ax is equal to 1. Let's first look at our constant terms. That's this one, and I guess that's it for the left-hand side. This gives us minus 4a. Now let's look at the x terms. We have a plus 2a minus 3a, so that's 0. That's nice. And we get 1. This tells us that a is equal to minus 1/4. Now we can go ahead and write down our particular solution. It is a, which is now minus 1/4, times x e to the minus x. And then in step 4, we just copy everything down. Y is equal to yc, which is c1 e to the minus x, plus c2 e to the 3x, plus our particular solution, which is minus 1/4, x e to the minus x. And there's our solution. And that's it. You now know how to use the method of undetermined coefficients to solve second-order non-homogeneous differential equations. You should now be all set to work through some practice problems on your own. If this video has been helpful to you, please consider subscribing to my channel. Keep believing in yourself and have a great rest of your day.